Welcome to the second of a three-part series where we explore the convergence of this series where k goes from 2 to infinity of 1 over k times k minus 1. In part 1, we explored this series using the nth term test and the comparison tests. When we used the nth term test, we discovered that it was inconclusive and could not be used to determine whether or not the series converges. However, when we applied the comparison test, we determined that the series converged. Now we want to take it one step further, and instead, let's revisit the same series using both the integral test and the ratio test in this part. And then the third part of this video series will explore looking at this particular series by examining the sequence of partial sums. Now let's look at applying the integral test to this infinite series. And recall that the integral test can only be applied if when we look at that general term of our series and turn it into a function, the function needs to be continuous, positive, and decreasing on the interval of x values that relates to the set of k values that we are doing our infinite series over. In particular, this function is continuous, positive, and decreasing. If you were to draw a picture of the graph just for x greater than or equal to 0, you get a picture that looks roughly like this. So we can use this integral test to determine whether or not this series converges, and let's do that. So we'll consider this integral from 2 to infinity of 1 over x times x minus 1 dx. When we think about our variety of integration techniques, we could use substitution, we could use integration by parts. This particular function that we're working with looks like it would work well to apply a partial fraction decomposition. So as a quick reminder, we factor our denominator into x times x minus 1, and then we set up our partial fraction decomposition to be a over the linear factor of x minus 1 plus b over the other linear factor of x. And then we can clear the denominators by multiplying both sides of the equation times the x minus 1, which is our common denominator. If we do, we end up with a new expression that says 1 is equal to a times x plus b times x minus 1. And we can quickly find the values of a and b by substituting in values for x. In particular, if we pick x to equal 1, then that means this term, b times x minus 1, will become 0 because we'll have a 1 minus 1 to give us a 0, and that just ends up giving us that a times 1 would equal 1, so a is equal to 1. Similarly, if we pick x to be 0, that makes this term a times x equal 0, and the second term would be b times a negative 1, which allows us to conclude that b is equal to negative 1. In other words, our partial fraction decomposition looks like 1 over x times x minus 1 could be rewritten as 1 over x minus 1 minus 1 over x. So now we'll set up our improper integral from 2 to infinity. We replace the function with its partial fraction decomposition. Then since we're working with an improper integral, we need to rewrite it as the limit as k goes to infinity of a definite integral from 2 to k of 1 over x minus 1 minus 1 over x. We can antidifferentiate each of those terms. The 1 over x minus 1 becomes the natural log of the absolute value of x minus 1. The antiderivative of 1 over x gives us the natural log of the absolute value of x. And before I substitute in and evaluated our limits of integration, I'm just going to use an exponent property to rewrite this as one logarithm. So recall, if we have the natural log of a minus the natural log of b, that can be rewritten as the natural log of a over b. So that's what I've done here. I've got the natural log of the absolute value of the x minus 1 over x. And now I can evaluate at my limits of integration. And that leaves us with the limit as k goes to infinity of the natural log of the absolute value of k minus 1 over k minus the natural log of 1/2. Now, when we look at this limit, remember that as k goes to infinity, the k minus 1 over k is going to approach 1. So that means the term, the natural log of that value, approaches the natural log of 1, which is going to give us 0. So this limit really becomes equal to the negative of the natural log of 1/2, but using a log property, we could rewrite that as the natural log of 2. If you don't see that, recall that the natural log of 1/2 could really be rewritten as the natural log of 2 to the negative 1, and our log property says we can take that exponent and bring it down in front as a multiplier, so we'd have a negative 1 times the negative, which gives us a positive ln2. Therefore, since our improper integral converged to the natural log of 2, we're allowed to conclude that our infinite series that we started with, where k goes from 2 to infinity of 1 over k times k minus 1, converges by the integral test. And we can take this one step further and find upper and lower bounds on the value of the sum using our formula from our integral test theorem in the book. In particular, the value of the improper integral provides us with a lower bound for the sum, and then if we take that improper integral and add to it the first term of the series, which in this case is a sub 2, those two things added together will give us our upper bound. So we know that this integral here is equal to the natural log of 2, and the first term of our series, we plug in 2 for k, we'll get 1/2, so a2 is equal to 1/2. If we add the natural log of 2, which is approximately 0.693, to the 1/2, we'll get our upper bound of 1.193, and then we have the value of our improper integral gives us our lower bound. So in part 1 of the video series, we showed by comparison that the series converged, but we didn't say anything about the size of that infinite series. By using the integral test, we've been able to argue that we know that the series converges, but we also have some bounds on the size. In particular, it's between about 0.693 and 1.193. So we can see that using the integral test is a little bit more powerful in this case to argue convergence than just using a comparison test, because we can actually say something about the size of this series. What if instead we had decided to apply the ratio test to this infinite series? Then we'd be looking at the limit as k goes to infinity of the ratio of successive terms. So we take our a sub k plus 1 term and we divide it by the a sub k term, and then we look at the limit to see what happens. And here I've color-coded the a sub k plus 1 and the a sub k terms just so that we can keep track of things a little bit better in this fraction that we're going to produce. So the a sub k plus 1 term is what we get when we plug k plus 1 in for k into the general term of our series. So we get a 1 over a k plus 1, and then we have that k plus 1 minus 1. So this numerator here in blue is our a sub k plus 1 term, and then we're dividing that by our a sub k term. Doing a little rewriting, we see that the numerator fraction really is 1 over k plus 1 times k, and we're dividing that by our a sub k term, which is 1 over k times k minus 1. And then we do a little bit more algebra. We flip and multiply by the reciprocal of the denominator because we're dividing two fractions. And then we see that we have some cancellation because these two k's will cancel each other out. So we end up with the limit as k goes to infinity of k minus 1 over k plus 1, but that limit is just equal to 1. And as we recall, when the limit of the ratio of successive terms is equal to 1, the ratio test is inconclusive. So we can see that the ratio test would not be helpful to us in determining whether or not the series converges. Luckily, we already know it converges because we've shown it with both the comparison test and the integral test, but had we decided to work only with the ratio test, we now would have to move on and try a different test to determine the convergence of our series.